Welcome to Chapter 9, the fifth screencast for gases. We're now going to look at gases at a molecular level in quite a bit more detail than we've done so far. And at a molecular level, gases, or ideal gases, are described by what's known as the kinetic molecular theory. Kinetic means moving, molecular obviously deals with molecules, and then theory is a sort of big understanding of how things behave based upon all of our evidence and what we think is going on. And it turns out there are several postulates of the kinetic molecular theory, well supported by evidence. And the first one is that a gas consists of randomly moving particles. These particles are the gas molecules or gas atoms that have no attractive forces between them. Now, in reality, real gases have a little bit of attractive forces between them, especially when the molecules are close. But the approximation of an ideal gas, we can treat the molecules as if they don't have attractive forces and they just move randomly or chaotically. These particles would be following a path, something like this. So we have a molecule, it travels in a straight line, hits another particle, bounces off, hits the wall of the container, bounces off, hits another particle, and it just follows some sort of chaotic, crazy path, moving in a straight line until it collides with another particle or the wall of the container. These molecules, these gas particles, are very small compared to the average distances between them. And in an ideal gas, in fact, we treat the particles as if they are infinitesimally small, as if they have no volume whatsoever. And again, not quite true in reality, but pretty good approximation for low pressure, not too low temperature conditions when we can approximate a real gas by an ideal gas. Another important postulate is that gas particles, when they collide, do so what's called elastically. And what that means is that there's no loss of kinetic energy during the collisions. So it's kind of like when two billiard balls collide and they have some energy coming into the collision, they bounce off, and in a perfectly elastic collision, all of the energy the molecules or billiard balls had coming into the collision, they have the same total energy afterwards. Now, real billiard balls will lose a little bit of energy every time they collide, and eventually they'll come to rest. But if molecules came to rest, gas molecules, then they just pile up on the floor and turn into a liquid or a solid. So they must be having no loss of kinetic energy during their collision. They must have perfectly elastic collisions. And then one more postulate of the kinetic molecular theory is that the average kinetic energy of the gas particles is proportional to the temperature of the gas molecules in Kelvin, of course. And one way to think of this is if we have molecules that are at a low temperature, i.e. they're cold, they have low kinetic energy, they're not moving very fast. And if they're hot, they're at a higher temperature, they have a higher kinetic energy. And if you double the temperature, let's say, then they have twice the kinetic energy. So proportional to temperature, kinetic energy of the molecules is proportional to temperature, providing we're in Kelvin. Now, the average kinetic energy of the molecules being proportional to the temperature in Kelvin is true, but we also have a specific relationship that the energy of the molecules, average kinetic energy, is given by the formula or the relationship 3/2 RT, where R is the gas constant and T is the temperature in Kelvin. And I won't try to derive this, but this is a true relationship, and then we will use this later on for some calculations. Important to note that at a particular temperature, all gases actually have the same kinetic energy, because kinetic energy is proportional to temperature. But note, of course, and just a reminder from physics, kinetic energy is 1/2 mass times velocity squared. If we have larger molecules that have a larger mass, then they have a correspondingly smaller velocity but the product 1/2 times m times v squared is the same. The kinetic energy is the same for these smaller molecules as for the larger. The difference in mass is compensated for, if you will, by a difference in volume. And if we have even smaller particles, then they have a smaller mass, but they'll have a correspondingly larger velocity. Sorry if I said volume earlier, all the v's here are velocity. So correspondingly larger velocity, and the kinetic energy will be the same for all of them. Now, some molecular reasons for gas properties such as pressure. Note that pressure is force per unit area, and the pressure of a gas is due to gas molecules colliding into, in this case, the walls of the container, but it could be colliding into each other, colliding into you or me or the tabletop or anything. And the pressure that the gas exerts is due to both how forceful the collisions are, how much force they exert, and how frequent the collisions are. If we have a lot of collisions, we get a higher pressure. If we have a small number of collisions in a given amount of time, we have a lower pressure. So gas pressure is due to both force and frequency of collisions of gas molecules on a particular area, in this case the balloon or whatever container that these molecules are in. Now, the molecules of gas that are moving around randomly, chaotically, bouncing into each other, exerting pressure and all that kind of stuff, the gas molecules don't all travel at the same speed. It's kind of like when you're driving down the highway. Not everybody is driving at the 55-mile-an-hour speed limit. Some people are slower, some are faster, and we have a range of speeds of drivers, just like we have a range of speeds of molecules. And the molecular distribution of speeds looks something like this, which is called a Maxwell or Maxwell-Boltzmann distribution. So if we graph the speed of the molecules versus the number of molecules at that speed, we typically get a graph that looks like this. It's not quite a bell-shaped curve, but it's slightly asymmetric curve, bell-shaped curve. We have very few molecules with a very low speed, more and more and more molecules rising to the maximum number of molecules at the speed indicated here, and then gradually less and less and less, and it tails off. Now, what does this average speed of molecules depend upon? Well, it depends upon some things that are maybe obvious and we've sort of talked about already a bit. It depends upon temperature, and it depends upon molar mass. And how these factors affect the molecular speed distribution is the following. If this is the molecular speed distribution at some particular gas at some particular temperature, if we go to a higher temperature for that same gas, the molecular distribution of speeds shifts to the right. And note that the peak also goes down a bit. So the average speed at the higher temperature is higher. We have more molecules with a higher speed, but we still have slow molecules. It's just that the distribution shifts towards higher in general or higher in average for speed of molecules. And then, of course, if we go to a colder temperature, it shifts the other way, so the curve shifts to the left. Notice that the peak gets a little bit higher because the molecules, we have a higher number of molecules at a lower speed, but we have the same number of molecules. So if there's a smaller range of speeds, then the molecules get kind of squished into this smaller range of speeds, and we have more of them at any given speed. This is the Maxwell-Boltzmann speed distribution for a specific gas, nitrogen, at 3 different temperatures, 100 Kelvin, 300 Kelvin, and 700. So here's 100, there's 300, and there's 700. And note the molecular speeds are in the many hundreds of meters per second, up to 1,000 plus meters per second. So they travel pretty darn fast. So that's the effect of temperature. Now, if we go back to our molecular speed distribution for some substance at a given temperature, and now look at the effect of, instead of temperature, mass. So we stay at the same temperature, but we go to a substance that has a smaller mass. Well, if it's a smaller mass, then the molecules travel on faster average, or their average speed is faster. There's more fast molecules than there were before, and this is because at a given temperature, the kinetic energy of both molecules or both compounds is the same, but if the mass is smaller, then the speed has to be higher to give the same average kinetic energy. And of course, we would also expect and find that if we have at the same temperature some larger mass, heavier molecules, their kinetic energy is the same, but their average speed will decrease. So note the similarity between the factors of changing temperature and having different masses of molecules. And then here is specific data, Maxwell distribution, for the effect of molar mass. All of these gases are at 300 Kelvin, but we're contrasting chlorine, Cl2, which has a molar mass of almost 71 grams per mole, with nitrogen, N2, molar mass of 28 grams per mole, and helium, 4 grams per mole. And you can see how shifted the speed distribution goes as the mass changes.